Very much for my introduction. So today I'm going to be talking about metal coordination compounds and electrochemical energy storage. Now this is just one aspect of the research we've been doing in my group. Oh, I can't actually affect that now. I'm going to try and get through this. Two big pieces of work that I've actually just tried to splice together in one coherent topic. So I'm going to have to race through some bits, I imagine, but I'll try and reduce my rambling. Oh, it's not letting me. Oh, there we are. Okay, so I'm in Lancaster University. Most people don't know where Lancaster is, so I'll just point it out on this map. So this is the UK. I hope you recognise that. Ireland missing, sorry, Mahal. We just got Northern Ireland there. And Lancaster is in this area here. We're just north of Manchester and Liverpool. And we hosted the 2018 Electrochem, the RSC of the UK Electrochem meeting in Lancaster, so I met many of the electrochemistry community there. And then, for more reference, here's London, here's Birmingham. So we were up north, we're before Scotland, we're near the Lake District, and it's a very beautiful part of the world to live in. So we can see the Lake District from Lancaster. That's Lancaster Castle and the lakes in the background there. Lancaster Castle, very important, of course, if you know your English kings and your history. Very important in the War of the Roses. Also likes to capitalise on its witch background. So there was some witch trials in Lancaster, and so there's the Pendle witch trail that runs through Lancaster itself. And I like to think of it, having lived in Oxford, I like to think of Lancaster as like the Oxford of the North, because we have the canals, the architecture is very similar, the colour schemes, everything. It's all canals running through it, it's got a river running through it, all pubs running along canals. When we have good weather, it is raining today, typical. Beautiful memorials, very beautiful settings to go around, basically, if you want to come to Lancaster. And then we're also very close to the coast, unlike Oxford, of course. So we get some spectacular sunsets across Morecambe Bay, which are very enjoyable to see. So it's a beautiful area of the world, very rural, but then also very well connected to the rest of the country. Mihal's done a great job of already introducing me, and he's already gone through my bio there, Oxford, Switzerland, and then Lancaster since 2014. So since I've been at Lancaster, I'll just go through this bit a little bit. When I started, I wanted to work on redox flow batteries. So I was working on redox flow batteries in Switzerland, but were conventional chemistries there, or ish, and scaling up. So we did some really innovative work in Switzerland over those 3 years that I was in Giro's group. But when I came to the UK, I had some ideas where I wanted to go with flow batteries and what I wanted to work with. I was a new PI, I had one PhD student who was really new, and he wasn't even in my group immediately. So it was just me starting out, and I instantly recognised that I was lacking any kind of network in the UK and infrastructure, and a lot of know-how was missing. So it's a very interdisciplinary subject, redox flow batteries. So I set up the UK Redox Flow Battery Network in 2016. Quite serendipitously, with funding from a different EPSRC centre, which had a program which related to flow batteries and networking. So happened across that and was able to work with it. So we ran a meeting last week, actually our annual meeting, and that's been growing in size significantly, especially this year because we were all online. So we had lots of international people joining us, which was fantastic. So that's been able to facilitate my network in flow batteries and try and get me more collaborators within the UK and outside of the UK, actually. And then I got some funding from the EPSRC for a first grant, and that was on my flow battery work. So I had a particular project in mind, which is what's described when the second half of this work is described. And as Mihal said, I've since had an ERC starting grant in 2018, but that's looking at CO2 reduction and electrochemical CO2 reduction specifically, but it does again capitalise on what we've been doing with flow batteries. So it's flow reactors, and it's all redox mediated carbon dioxide reduction. So I'm really using know-how from across the spectrum of all my history in my CO2 grant. About my group, so my interest, and they have to do it too, is electrocatalysis. So we're mostly looking at CO2 conversion, but also look at hydrogen, oxygen, water, all these different catalytic systems as well. We also work on electroanalysis. I think these are ideal for student projects. But also we can't really do effective electrocatalysis without having a a really robust analytical setup as well. So we look at electroanalytical methods of doing things, but we also have our chromatography, NMR setups, and all these different things that we have to facilitate our CO2 reduction work. And then I have always got my interest in electrochemical energy storage, but who doesn't these days? But we particularly look at redox flow batteries. So it's really large scale energy storage systems is the intention, but we do it all on the lab scale, small scale system. But we have redox flow batteries at the heart of what this topic is about today, but I also have interest in supercapacitors, batteries. And more recently, I'm looking more at the small scale. I'm going to sort of wearable technologies and flexible batteries and looking at where we can use our sort of mediators and our different organic chemistries in sort of wearable technologies, going the opposite end of energy storage. But what I do have at the heart of everything we do is that I really want it to have a sort of sustainable focus and an ethical focus to the work. So it's really important to me that when we are looking at new systems and new technologies, that's always in mind. So we want to make sure that the synthetic routes are nice. I'm a bit of a chemical phobe, so for me it's better for the synthetic route to be very feasible, to be scaled up, to be something that's sustainable and not nasty for the people doing it. And then the materials we use, that I try to find things that are actually going to be here in 100 years' time, something that's very much accessible and available for us. So that's at the heart of everything that we're doing here in Lancaster. So this is my group. We're just missing one person here. So missing my PhD student, Beth. So there is another female person in my group. But unfortunately, she's not in this picture. But this is my group as it stands now, PhD students and postdocs. Well, as it was in October 2019, still the same makeup, but with one extra person. The work I'm going to be discussing today is from Craig Armstrong, so Dr. Craig Armstrong now. So he's my first PhD student, and he graduated in, or he qualified in December this year. So now he's a postdoc in my group, thankfully, because he knows what everything is. And the other part of this work was run by Dr. Ross Hogue, who is an outstanding synthetic chemist, and he got a Marie Curie fellowship and went off to Leiden, unfortunately. But he was in our group for a year and a half, and is outstanding synthetic chemist, really, really good, and fantastic guy as well. So do look out for him. I think he's an up-and-coming star. So unusually, probably because I'm going to run out of time, I'm going to start with my conclusions. While you're all paying attention, I hope, what we're looking at, just to remind you, is metal coordination compounds and electrochemical energy storage. So the conclusions of what I'm going to be saying today really are relating to these two compounds here. So you've got cobalt azole pyridines is the first half of the work I'm going to cover, and then metal dithiolines is the second part of the work I'm going to cover today. And what we're looking at is trying to really affect redox potentials and solubilities and properties relating to these metal coordination compounds to improve the energy density of a flow battery. Now I'll be going into a bit more what a flow battery is and what the principal properties are in a minute, but just to indicate where we're going and what you're going to be looking out for. What we did was we manipulated these tridentate ligands and substituted sort of one or two of the moieties from pyridyl to a pyrazole structure instead, and we had these mixed ligands to try and affect the redox potentials. So we tried to weaken the cobalt nitrogen bonds on some aspects of that chelate. And we were able to do that. We were able to tune the properties of those ligands and get considerably higher energy densities compared to a tridentate bipyridyl to pyridine system instead. But what we also demonstrated was that, oh, this doesn't change from earlier, is that in that work that we could actually get some flow battery data that was okay, but if you don't have the right equipment, then you really, really have rubbish data, and that we got significantly better data when we improved our equipment and our analytical facilities for doing the flow cell system. And how important that is on what you really qualify as your data. So you could be dismissing systems because you haven't got the right setup. And I think it's really important that you make sure and take the time to develop your setup to enable your results, because you could be coming up with fantastic metal coordination compounds for your system, but then they're not being properly demonstrated from your unoptimized equipment. So we really found that was critical conclusion to some of our work. With these metal dithiolenes, we were again picking up on that metal chelate effect and the influence of the ligand on the electronic structure of the metal center. So metal dithiolenes are what are called non-innocent ligands, so pyridines actually, but redox non-innocent ligands can share the electron density across the ligand to the metal center. So in a way, you can access metal centers or metal oxidation states, or seemingly so, that aren't normal. So, you know, like vanadium 6 or an iron 4 system, for example. So we wanted to see if we could capitalize on that and try and access some oxidation states that were unusual and quite separated to give us big redox potentials, potentially. But what we found is that you know, voltammetry is a really poor indicator of whether you've got very good performance, and I think everybody knows that anyway. But in a battery system, it's really, you could have a full cycling battery and it has really terrible performance, but when you interrogate the individual redox couples within that system, you can find ones that are really, really stable, and you can find ones that are really, really poor, and you can indicate, you can identify what the weakness is in your systems. We did a rigorous study of all these metal dithiolene complexes to establish which were the promising couples within that system with multiple redox states. And in the big conclusion, I suppose, is that the one thing we've realised, having done 5 years of work in this area, is that we've come to the conclusion that non-aqueous batteries are really not a viable viable route towards affordable or flexible flow battery energy storage, at least. So there's possible outlets within, you know, downsizing and smaller systems, but really within flow battery and energy storage and big scale storage, which I'll go into in a second, it is not a really feasible route. So I think we're going to be drawing a line on non-aqueous chemistries for flow batteries going forward. But I really think we've rigorously understood the complexities and the advantages and disadvantages of the system as we've gone along. So I teach a module on energy storage to fourth years for master's level students, and I was open with this slide because I quite like it. But Renewable Energy Policy Network from 2015 indicated that for the first time in 4 decades that carbon emissions had remained stable in 2014. So in 40 years we had stable carbon emissions in 2014. This was attributed to the increased penetration of renewable energy. Now this trend continued then on to 2015 and into 2016. Unfortunately, then it came to an end. But 3 years on the trot, we had sort of stagnant or stable carbon emissions related to energy systems. It related to renewable energy penetration, and that has vastly increased over the last decade, as we've seen. In 2016, the UK had 25% of the electricity supply coming from renewable sources. Now, that includes biofuels and bioenergy as well, and hydro. The amount of that was considered to be coming from intermittent renewable energy systems was 15% roughly. 15% of energy of the whole electricity generation in the UK is a significant amount, and you need to be able to offset that within your energy network. Now, in 3 years, the renewable contribution has increased 10% to 35%, and that intermittent renewable energy supply has increased 7% to 22%. It's around 22%. In the COVID crisis, we actually were actively off. We were just running off renewable energy at one point for electricity. I'm on a renewable tariff, and we were requested to turn as much stuff on some days where they were expecting a surge of energy on the network, which they couldn't account for because people were using a lot less electricity generally. So we earned a whole 20p in turning as much stuff on in our house to try and account for the amount of intermittent renewable energy that was on the electricity network that they couldn't do anything with and they needed to get rid of. So it's getting increasingly problematic that we have all this excess energy on our networks because that renewable penetration has increased so much. It's also getting to the point where in certain areas of the country, you're seeing people are unable, the electricity suppliers are unable to permit renewable installations because they can't facilitate it on the actual infrastructure of the grid. So the infrastructure is not good enough, and the capacity for storage is not sufficient to permit more renewable penetration. So while we're trying to move to a greener system, we really need to account for it in our energy storage network. You can't go forward with a renewable green society without effective energy storage in our network. Yeah, all these smart grids, all these future energy networks that were being designed, you can see them here integrating all these solar power plants, these wind power plants, smart houses with panels on their roofs, buildings in the city, electric vehicles were still being considered, all this stuff in the smart grid of the future. There's a conspicuous lack of energy storage in this system. So where is the storage? Where is what is facilitating and allowing that transition from renewable generation into a control center, into distributed energy storage? So it's weird to me that the UK had its first energy storage conference the year I came to Lancaster, so in 2014. It was the first time the UK was really considering, from a research perspective, how energy storage was going to feature in our energy network, because there had been such a surge in this renewable penetration. It was very much after the fact. Now, we're not behind that much on renewable energy storage systems. We have a whole range of technologies, but we do have established technologies, so pumped hydro and compressed air storage, and powered with gas, which is electrolysis, water, trying to generate hydrogen, putting that into our gas networks. There's this whole area now of synthetic fuels. So this is all storage which is really long duration that we can sort of store separately to the generation. So it's really flexible energy storage here. So synthetic fuels is a relatively new area. So we're trying to convert carbon dioxide or other materials into a fuel that can be a liquid fuel or a gas fuel. And then the other end of the spectrum is where your storage capacity is low, but your discharge time is really fast. So this is for ripples in the energy network. So you've got flywheels and supercapacitors, which are ideally suited to that technology, so to that offset. So we want to be able to account for any surges or drops in the energy networks for a large-scale infrastructure. So we use these fast delivery methods. Whereas electrochemical energy storage really features here. So it can go from the fast delivery to numbers of hours across the day. So you're roughly looking at sort of a one day discharge, charge-discharge cycles at the top end of the battery system, and then you've got really fast back and forth at the lower end of the system. But as we all know, electrochemical energy storage is really diverse. So this is batteries just being considered in one lump here in the energy storage framework. And what we're seeing more and more is that people have gone, all right, batteries, well, we know what batteries are. We've got batteries in our cars, we've got batteries in our phones. Why don't we just extrapolate that technology and make it an energy storage system that works? But it's not that simple. You can't just extrapolate battery portable technology and make it work for the grid. So lithium ion is really being peddled now, not just for electric vehicles and for portable storage and all sorts of things, but it's now been pushed as well for the grid energy storage network. And it's not necessarily the right fit for that system. So we need to really consider energy storage rather than battery storage when we're thinking of scaling up electrochemical systems, as I've said here in this title. So energy storage, not battery storage. Now, what we really want to think of, what are the features, what are the attributes of an energy storage system that we need to facilitate renewable energy on our network? And that means we need to be looking at the 4-hour plus market, really, rather than that really quick market. We've got things that sort of count for the quick ripples and energy deliveries, but we need to be thinking about isolated networks that can deliver a steady output and store a steady output of energy over many hours in the day. So it's something that's going to fluctuate across the day. And we also need to be thinking about large scale systems that can be centrally managed. So something that, you know, is flexible and diverse and can be scaled centrally in a sort of big network. So it's lovely to try and get some nice pictures of energy storage systems. They always just look like shipping containers and solar panels next to them. So they all look the same. So there's no indication here of what type of energy storage system this is, because all the batteries are sort of being looked at in the same way, in this sort of containerized manner. But we are still looking for something that can be scaled easily and centrally managed and is safe. So that brings me to flow batteries. So in a conventional battery, what you have is all your material is contained in one battery cell. So you've got solid materials and they're back and forth through a separator of some description ionically, and then you've got your charge going through. So all your material is inside this one container. Your electrodes are in there, your electrodes are intrinsic to the performance of the battery. Everything is in one space. Now, so if I want 1 hour of energy storage from a battery, I need one battery that can last an hour, but everything in its entirety. If I want a redox flow battery that lasts an hour, then I'll need to consider the power and charging outputs that I want to be getting from my system, and that's where the battery center comes in. So that's when your electrochemical cell comes in, but this is simply operating as a means to charge and discharge your redox mediators. Whereas your energy storage all comes into these tanks on the other side. So your electrolyte reservoirs. So this is where your redox mediator is stored, and it's the concentration of that indicates, and the volume of that indicates how much energy you've got available to you. So 1 hour of storage might have this volume of electrolyte. But then if I want to scale that up to many hours and try and have a more flexible system, a conventional battery is just going to have to be multiplied as many hours as you need. So maybe 6 hours here. You'll have to multiply the entire system to try and get that battery, to get all your electrodes, everything needs to be scaled up for that increased storage capacity. Whereas a flow battery, you simply need to increase the volume of your reservoirs. So you've got all your energy storage is here in these reservoirs. You don't need to affect your electrochemical cell. Now this is your power output and this is your energy storage. So the two things are decoupled in a flow battery, and it's an inherent flexibility that's really important when we're going forward with energy storage rather than battery storage. Now the state of the art in the system is the vanadium redox flow battery. So there is already a commercialized established technology out there for redox flow batteries. Now this system uses all vanadium. So it has vanadium 2, 3, 4, 5 across the whole system. And your negative side, should we call this the negalite? On your negative electrolyte is where you've got your vanadium 2, 3 couple oscillating. And then on your positive side, you've got your vanadium 4, 5 species oscillating back and forth. Now there's a 1.26 volt potential difference between the vanadium 2 and the vanadium 5 species. And so that's how we get our energy back from the system. Now all of this charging happens in an inert electrochemical cell in the middle. So you have a stack of cells. The liquid is pumped through these cells, which are separated by a membrane, which is the naphtha membrane typically, or some kind of proton exchange membrane. And the electrodes are just there supplying and taking away electrons. They're not actually part of the reaction in a way. They are their workhorses. All the reaction stays in solution, and this adds to the longevity of the battery. So you've got many advantages of a flow battery. You have your independent power and capacity, like I've already stressed. You have that long duration storage of more than 4 hours typically. You can also flip and switch your battery without any effects of partial charge states. So it can be charging and then it can instantly start discharging depending on what your needs are. So when you've got fluctuating energy supplies, it's really, really adaptable to that. Because you typically have redox species all in solution, you'll have reversible and stable systems and longer lifetimes for your battery because nothing is depositing and stripping. Obviously, there are zinc batteries and chromium and iron batteries, all different kind of metal ion batteries that also involve metal stripping. And these are hybrid flow batteries and they're also effective as well, but they don't have that same longevity. But there are inherent disadvantages to a flow battery, and that's what you've got your low energy density, which is critical because you're going to have a low energy density because you're so dependent on the concentration of solution that you can acquire. So a vanadium battery can typically get to about 2 molar concentrations of vanadium before you start getting adverse effects from precipitation of the vanadium in solution. So you're limited to that 2 molar or maybe 2.5 if you put in certain additives of concentration of vanadium. And that's a cap, that's a really low cap. So you're looking at an order of magnitude lower energy density than you are for a lithium-ion battery, or like half the energy density of a lead acid battery, but the lifetime and the depth of discharge is considerably higher. There are positives and negatives to all these different designs, and it's trying to marry them all up and trying to influence one and try and get a system that has all of the model behaviors. You also have expensive electrolytes and expensive membranes in the system as it stands. So you're looking at a system that's just not affordable as it is, and it's not going to dislodge or compete effectively with lithium-ion as it stands. But what you do have is a lot of things to play with. So it's a really, really playful material system. I haven't even started to talk about research, and it's 24 minutes in. We have our the energy density, which is represented by E here, is affected by, if you look at Faraday's laws of electrolysis, it's really that basic. The number of electrons in our charge transfer, the voltage of the cell, and the concentration of the active species in solution, all directly proportional with the energy capacity of your flow battery. So if we can modulate any of these, if we can design redox species that have increased voltage windows and potentials, and also higher concentrations in solution, or indeed have multiple redox events in a single transition, then we can double or we can triple our energy density really quickly. So we have ways of manipulating the chemistry a lot more when we're within this kind of system. So we've been looking in my group at new chemistries for redox batteries with that principle in mind, and we were looking in multiple directions. So at first we thought, right, let's move away from water. With water, you're limited to this voltage window. According to the thermodynamic stability region of water, you've got 1.23 volts. Kinetically speaking, you've got more about 2 volts, like we see in the lead acid battery. You can work, if you can suppress the oxygen and the water splitting reactions, then you can operate in a lot bigger area, but you're still limited, and you're still only ever going to reach that 2 volt sort of potential in your system. If we move instead to a solvent-based system, so a non-aqueous solvent, then you're looking at wider potential windows. So immediately you could have species that are well separated in their potential window. You can play around the chemistry. You've also got a lot more chemistry to play with, a lot more metal organic systems that you can manipulate and use in a non-aqueous solvent. So you can immediately increase the cell potential, which will affect that energy density. What's more, you can also create species with multiple redox events, and if you can get those redox events to couple up very close to each other, then you can have, you know, double or triple the number of events. If you charged all the way to here and then discharged all the way to here on one side, then you would have, you know, 2 or 3 ends in your system. So that again increases that energy density. So what we wanted to try and do was explore chemistries that would achieve these properties. Now I'm just quickly remark on 2 things. So in that system that I was showing you, you've got 2 types. You've got an asymmetric battery or a symmetric redox battery. So these are pure flow batteries now, where all the redox species are in solution. You also have a hybrid battery where you've got 1/2, which is metal deposition in the battery, and then the other half is all staying in solution. Now we're just looking at the pure redox battery, so everything's in solution here. For an asymmetric battery, you'll have 2 redox materials. You'll have 2 completely different redox materials in your positite and your negalite. They're unrelated, and you only need at least 2 oxidation states for A and B, respectively, in order for that to work. And that has advantages in that there's more opportunities for study, so you can look at all sorts of species in A and all sorts of species in B and mix and match them. Because your redox properties in A and B are also independent of each other, so you've got the advantage there of you know, not having the same kind of decay mechanism for one, or once you go into an oxidation state which is more complicated, then you're not going to have that suffer in your system, because you can just use the stable redox couples. And for a symmetric battery system, it depends more on a single redox species that essentially disproportionates into 2 forms. So you might have a reduced form and an oxidized form of that central species. So you need at least 3 oxidation states. So vanadium's a symmetric system because it has 4 oxidation states in solution, in aqueous solution. And that has reduced membrane constraints. So that the huge advantage of a symmetric system is that when you get crossover, which you inevitably do because of thermodynamics, you're not going to lose capacity or contaminate your battery. Because as soon as you get crossover in an asymmetric system, then both your electrolytes are compromised. And you will need to do something to rebalance the system. If you have it in a symmetric battery, then you're usually just countering one on the other. So whatever goes in one way comes out the other way, typically. So you have simplicity of design as an advantage to a symmetric RFB. And we've exclusively looked at symmetric RFBs and non-aqueous chemistries in our work for the last 5 years. So what we looked at in four different systems we've looked at over the last thing. I'm just going to focus on these metal coordination compounds today, but we also looked at cell characterization. So we have a paper out, Journal of Electrochemistry. Well, I don't know when it's going to come out. It's been with them for a while now, so it's meant to come out soon, which is just using ferrocene as a means of characterizing flow cells. And we've also got a metal-free system, Croconic Violet, where we explored this system, and it has multiple redox events, so we're able to do a symmetric batch using this complex here. It wasn't fantastic performance, but it demonstrated and we learned a lot from it with regards to the stability of these radical states. But metal coordination compounds have a lot of promise because they're a lot more stable, and the chelation effect, the metal ligand effects, really stabilize oxidation states, and that metal center is really robust when it goes to higher or lower oxidation states. So there's far more ability to manipulate metal coordination compounds and explore them. It does, however, mean that they're usually quite bulky materials, which then has a negative effect on your energy density in that sense. So without further ado, I'm going to go into the actual results. How much can I get through in 20 minutes? Okay. So the first lot of work we did when we first started my group was to look at I was inspired by a paper by Chevalier and Bretzel in Organic Chemical Actor, where they had cobalt complexes with these mixed moiety ligands. So they had azyl pyridine ligands. So they've mixed them all up. And they've been looking at how this had affected the redox potentials, and they've been playing around with the structure as well, and the different alkyl groups and whatnot on the system to see how it affected the redox potentials of this cobalt complex. And it had multiple redox events. So when I saw this study, I thought, do you know what? That's a candidate for a flow battery there. You've got a symmetric flow battery because you had at least three oxidation states that we could play with, and they're really, really good redox chemistry. So we explored what looked like the most promising of the couples in this system. So one was a pyrazole couple, and another one was a triazole system. So we looked at these two systems initially, and this is what Craig started his work with me. And we compared it to a terpyridine chemistry. So what we were making were cobalt complexes with tridentate ligands to increase the stability of that cobalt to ligand structure, so we wouldn't detach it, and we could affect as well. We could play around with which moieties we had in our ligands in order to manipulate the redox properties, the redox potentials of that cobalt center when we were going from a 2,3 oxidation state. Now, what we did, so in the paper, in the Chevalier paper, they had these two complexes with the single substitution, but then what we thought is we'll do a double substitution as well and see how that works. We were able to synthesize the bis-pyrazole pyridine system, so it's still tridentate, but we had two of the pyrazole systems in there instead. But we couldn't do this for the triazole. We couldn't isolate the ligand. So we managed to look at these four systems anyway with the cobalt complex at the center. So what we have here. And you can see the voltammetry for these systems is really good. Now, we weren't expecting such good voltammetry. Well, I was, because I'd seen it in the Chevalier paper, but you shouldn't be expecting such good voltammetry for the cobalt 2,3 transition because it's a high spin to low spin state. But we actually end up with really good reversible chemistry for all of them on a gold surface. What we have here is the terpyridine system, so without any kind of modification to the ligand structure, is all pyridine based. Moving towards a single substitution pyrazole, the triazole, is ligand 4, and then our ligand 3 is our doubly substituted system. And what we got, and which is what we're really trying to achieve here, is that shifting redox potential, because when we were shifting this positive redox potential, because this is the only one that's going to be affected really by the modifications of the ligand relative to the 2-1 couple. We're going to see increased cell voltage for our battery systems that we want to look at. Of course, it didn't matter which electrode surface you were working with, so we were working on gold in some instances, but when we looked on glassy carbon, you see now that our doubly substituted system has really poor. This is a bit more what you're expecting for a cobalt 2-3 transition, but we've got more reversible voltammetry on a carbon electrode. So it does matter which surface you're working with to get the kinetics right on this. But what we still saw, regardless of that, was a transition from a 1.07 volt system to upwards of 1.8 volts, depending on which system, or 1.5 volts, depending on which system we were looking at. So we really increased that cell voltage in our chemistry, or potential cell voltage. What's more, we also increased the solubility. So solubility wasn't great of these complexes, which is going to massively affect the energy density of our system. So for the topyridine, you see the energy density is really low at 2.6 watt-hours per litre. But by manipulating the ligand structure, we could get something that's on around 12, which has potentially 12 watt-hours per litre, which is on a par with a lot of organic electrolytes as they're being developed at the moment. Now, I'm not going to go into the chemistry, the inorganic chemistry, or anything of this now, but if you run a really good explanation of the underlying inorganic and physical properties of making this shift and what it's doing to the redox potentials, I recommend this paper. This came out just after we published our work, and it's the same topic essentially, but a lot more rigorous, and it has a computational study underneath it as well. But we moved on to really, well, the voltammetry tells you one thing, but we wanted to look at what we could get from the cell performance. So we looked at the H cell, which is a static system, which is really not ideal for a flow battery. It's not what we'd have normally, but it gave us an idea of what we could get cycling back and forth between the 2-3 and the 2-1 oxidation states. So we were separated by an anion exchange membrane, not a cation exchange membrane. So we wanted to make sure that we limited crossover through the system, even though it was a symmetric system, so it wasn't that detrimental. But we found the anion exchange membrane was best. But obviously there are huge issues with this setup immediately. So the membranes are designed for aqueous. There are no non-aqueous membranes. There's a large separation of the electrodes, so that's a significant and a low conducting acetonitrile solvent. So you're looking at a big significant cell resistance immediately. So you're already affecting your behavior. And these graphite rods that we used had low surface area, and there's very limited convection because it's just from this magnetic area. So H-cell testing is not ideal for evaluating redox couples for flow batteries. We got good stability over 40 hours, but this was at an extraordinarily low current density of 4 microamps per centimetre squared. So really painfully slow charge-discharge profile. So you can see the hours here. To get our 10 cycles, it took 40 hours. In a glove box as well, because we were working with cobalt complexes, which was very sensitive to oxygen. So we worked entirely in the glove box for this. Well, we got our 3 oxidation states, and by running it very slowly, we were able to get a very good voltaic efficiency. So you can see the charge and discharge voltages are very much hovering around the theoretical cell potential, and so that was very high. And a coulombic efficiency was very good as well. So our energy efficiency is largely affected by the voltaic efficiency. So, and the coulombic efficiency here, but we can see it's a really good response. We had the same typical H cell response for all of these things. I'm not going to show you all of them in detail, but we've got a good response. But here's a summary of what we saw. But really high coulombic efficiencies, extraordinarily slow charge times, but they were in line with what we were expecting. And a reasonably good, for a first time Scanlon and H-cell system, we had very good voltaic efficiency. So the overall energy efficiencies were around the 75% mark in general. Now, what we tried to publish this as it was, and we weren't allowed. The referees wanted us to do a flow cell study, which is fair. But we didn't have the capability for a flow cell system. And I knew that we couldn't just apply it to an aqueous system because it wasn't designed for an aqueous system. So we were going to get bad performance no matter what. But we had to create one. We had a month to do all these changes to the paper. They just wanted a flow cell. It seemed simple, but it wasn't. So we did an emergency flow cell, and we made it out of 3D printed polymer. but we hadn't really troubleshooted what we needed, and we didn't know what we needed until we were trying to do it. So we had far too big a volume of electrolyte for a starter to what we could actually make. So it was really tricky to try and be able to make a big batch of this cobalt complex in order to have a sufficient concentration and volume of electrolyte for our cell. And it was really basic. It was 3D printed. It was just a single flow-through system with a basic membrane. So we used that. We set it up. We had our peristaltic pump, so it was okay. But there were significant issues. We learned so much from this process, even though at the time it was stressful. But leakage from the current collectors, large volumes required, really poor compatibility issues with the polymers and the solvent, high cell resistance, warping happening because you were using acetonitrile. It's not a great thing, and it was charging and discharging seemed to be affecting. It was swelling on long-term exposure to the solvent. Disassembly was really difficult, and then it was really hard to clean as well. So it was not an ideal system, but we managed to get some results for the paper anyway, even though I was loath to hand them in because I thought, well, this is not representative of the performance of these materials because they're not in an ideal setup. But nevertheless, we achieved a much better, because we were using 4 milliamps in the static cell. So we managed to, go up 2 orders of magnitude, flow it, get cycling behavior. We see a really rapid decay, but we got about 20 cycles in for one of our complexes. And we were also able to really push it and get 1 milliamp per centimeter squared out of the system as well. But you see an even more significant decay, because when you're charging it at high current density like that relative to what's in the system, you can see the voltage separation massively. So you're plummeting your voltaic efficiency immediately because you've got so much resistance in the solution. You're separating your charge and discharge, and when you're overcharging like this as it's happening, you're also going to start decaying your material that's in there, and really affecting the ligand structure and the complex integrity. And yeah, we saw that because when we had, this is what it looked like before cycling, and then we looked at what was going on in the system after cycling, and you could see that the 2-3 couple had just gone to pot. It did not have that same performance, and we'd also deposited something on the electrode surface. There was all sorts of things going on with that complex, so it did not do well to have that high current density in a poorly designed system. Now, since then, we've done a lot of work developing our flow cells. We left that, we were able to publish it as it is, and we moved on to other work. But I'm just going to hark back, because in Craig's thesis, he's since gone back with our more recent designs for a flow battery cell, which is from the Brushette group, who are fantastic, who've really gone to town with exploring optimized non-aqueous flow cells. And this non-aqueous flow cell system, which we've got now in our lab, we've designed it, we've also tweaked it a bit for our own system, is a minimal volume cell, and it's got chemical resistance, and it's got minimum cell resistance too. So you're really already helping your system by reducing all the resistances in the system. It's got better flow dynamics in there. Everything's just geared towards non-aqueous chemistry. So you're already on a better footing. So we explored one of our old complexes again at that higher cycling rate. So we did it at 1.25 milliamp per centimeter squared, and you can see we managed, where we could only manage about 20 cycles previously, we were able to actually get to 100 cycles in this system. So just by changing our setup, we were able to get much better performances. And this was all, again, because this is done a long time after the study, we've used what we had left over, which is a complex which was probably the one where I showed the worst performance. So I wasn't expecting great performance here from the flow cell, but we actually got stability for a lot longer. And I think about a 60% energy efficiency overall from 100 cycles. So we suddenly ended, but the cobalt azole pyridine demonstrated to us that we could manipulate the energy, the tunable response of our behavior by playing around with the ligand structure. So there's a lot of development, there's a lot of playing with structures that can really give us different oxidation states that are exciting. But we were able to see that we're completely limited by the low solubility of the species. The membranes are unsuitable, the sensitivity of the kinetics of the cobalt 2-3 couple even though they are stabilized by that tridentate ligand, so you're unusually getting reversible chemistry in some contexts for what should be an irreversible system. But what's really important to consider is that, yes, tridentate ligand really stabilizes that metal center, but it also gives you a lot of bulk to your structure, and that plummets your energy density, because your size of your molecule really affects the energy density of your solution. So from a gravimetric perspective, it's really, really cool. So we look towards smaller ligands to really try and bring down that cost, that bulky cost. So I'm going to race through 5 minutes. This always happens. I'm going to race through this bit about metal dithiolines now, but it's building on the work I've just been discussing anyway. So we looked, so this is when Ross joined me, and this is my EPSRC first grant concept that I wanted to try and explore, and it was redox non-innocent ligands. And redox non-innocent ligands are ligands that contribute to the energy density, the electron density of your metal organic structure. So that means that you can go beyond normal thermodynamic stability. So what they thought was they were achieving these weird oxidation states in the past. They were actually achieving energy. Some of the electron density was going on the ligand instead. So it's this crossover, this is blurred line of where the ligand is doing the work versus where the metal center is doing the work. So, like I said, in the past, when they started looking at this in the 60s, they thought they were achieving this vanadium 6 species here. Sorry, something's happening. Oh yeah, someone's trying to share the screen. So we had this vanadium 6 species here, was what they thought, but it turned out it was the dithiolane oxidation that was happening. So you have this reversible oxidation of the ligand taking place. So while you get this normal consecutive, oxidation of vanadium 2, 3 for your vanadium center, you then start to oxidize selectively the ligands instead. So that means you can access these other oxidation states. Now, this work has been studied, so we wanted to look at where this could be applied to redox flow batteries to see if we could access some unique oxidation states that would really push out the voltage limits of our battery. So we made these dithiolane complexes with the malonitrile ligands, so that's with the cyano groups here, and the two thiols, so the two sulfur, what they're called, atoms, and we came up with a really nice synthetic route. I say we, that was Ross that came up with this really nice synthetic route relative to what was in the literature. And we made a variety of these with different metal centers from the first row transition complexes, and we coupled it with a TEA counterion. Now, this species, the vanadium MNT, has already been explored for redox flow batteries in the past, but it was very rudimentary, so it was very basic, and it was sort of just hinting towards the possibility of it. So we've capitalized on the suggestions of this paper to try and see where we could go with other metal centers as well. So we synthesized all of these, so the vanadium, nickel, iron, copper, and cobalt centered systems. The vanadium has these 3 oxidation states, because we know vanadium has multiple oxidation states. So we, in theory, if you could use the whole range, you've got a 2.27 volt system. Whereas all the others have 2 oxidation states that you can use. You've got a nickel 2-1 and a 2-3 system. You've got 2 iron systems, although there's something going on here. You've got 2 oxidation states for the copper, and then 2 for the cobalt too. So all we need are 3 distinct oxidation states to have a symmetric battery. So we wanted to use all these. We explored them in that way. Here's a summary of our responses. So we did exactly what I was showing you before, but with our now optimized electrochemical cells, and we were able to get these cell potentials. Too much information, let me just summarize it. So our best systems, theoretically speaking, are the vanadium, which could give us possibly 16 watt-hours per litre if we were able to capitalize on that maximum voltage, whereas the copper system had the highest solubilities, just shy of 1 molar, and that manipulation, so even though it has a really low cell voltage of 1.12 volts, we could still get, because of the solubility, of 14 watt-hour per litre energy density. So this is just demonstrating how those little parameters can have such an effect on the energy density of your overall system. So we started doing the battery cycling, we explored it in that sense. So we went beyond voltammetry, where you just get an idea of what to use. And we looked at this one which is similar to the Capellino one. So this is our setup, a symmetric battery, looking at these two coupled here. The vanadium 2 to 2, yeah, hang on, that's a 2 2. So the vanadium 3, 2 to, oh, sorry, start with the 2 minus, and we go to the minus and the 3 minus of the system. And we got really rubbish battery cycling. We can go for a bit. We can go for a number of hours, we can go for a number of cycles, but generally, after 50 cycles, we really decay. And that behavior is exactly what Capellino saw. They had a really good charge profile, but then the discharge was awful. The discharge is sort of multiple plateaus, which indicates that you've got multiple redox species in the system. So you've got different things going on in there when you're discharging. So at least that was in keeping with what we'd seen in the literature. And you see we got really poor Coulombic efficiency, because when we were charging up to this date, we were only getting this much charge back in our reduction when we were discharging the battery. That's my timer. Voltaic efficiency, however, was really high, so, but that really depends on how you interpret the data. When we looked at, so that's the whole cell, and it's not very good. But then we decided to look at the individual redox couples, because that's the best way to interrogate which one's decaying in battery. So we charged up so that we would have a system that just ran on a single species. So you can either charge to the 1 minus or the 3 minus system. So we made a 0 volt battery, which just operated so that on both halves of the battery you have a 3 or the 2, and it's just going 3 and 2, 3 and 2 in both sides. So it's a 0 volt battery. We did that for the 3 2, and you see we've got a really stable performance from what was our negalite in our system. But then when we looked at the corresponding positite, the 2 1 transition, 2 minus 1 minus transition, we see that we get the rapid decay. So that indicated to us that the problem species in our battery was actually the positite for the vanadium. And we looked at this with UV-vis analysis as well, and we can confirm that within minutes we were descending back into our starting material. So the vanadium 1 minus that was being generated in the positite was immediately decaying back into being the vanadium starting material. So that's where that capacity loss was coming from. Now, we did this for all our species, and the nickel, you see, we've got terrible voltammetry for the full charge system. It looked like it was going to be really good from voltammetry, but then we did the battery, you get a charge and you get terrible discharge. Why? Same thing, but in this case, flipped over. So in this case, our negalite had terrible capacity, whereas our positite was really, really stable, relatively, not very, it was obviously decaying, but relatively stable compared to the negalite. So when you get the single couple performances, you can see how they differ massively from one species to the next. And again, we confirmed that with UV-vis, and the overall performances are given here. So when you're looking at the full cell of the system, this is the behavior again. So you get, this is the normalized performance of the battery, the energy performance of the battery, and you can see the copper is really consistent, but then you've got vanadium sort of giving you the best performance, and nickel's giving you terrible performance. But when we look at the individual negalites and posilites that contribute, our negalites, we get the best performance from the vanadium, and in the posilites, we get one of the best performances from the nickel. So that means that we're looking at a system now where we can identify where we can actually do mixed ligand system, or mixed complexes, and have an asymmetric battery, capitalizing on the good performance of the vanadium, for example, and the good performance of the nickel, and use them with different systems. But I haven't gone into that here. You'll be glad to hear I finished. So the novel chemistries, what we've seen with dithiolines is that they were a low molecular weight, so that's a really good attribute, and we could get more than 2 redox couples and a good solubility for these complexes. So they're really exciting. I still think they're really nascent in their study, but they did have short lifetimes, and their stability was dubious. Even when we had our most stable couples, they were still breaking down. And there was significant crossover through the membrane. So if we tried to do the mixed, if we tried to do an asymmetric battery, you were going to have detrimental effects. But there's a lot of potential for developing these. So this was just the simplest form that we had now. We're looking at lots of different kinds of dithiolane ligands now to see where else they can be applicable. So I think there's a lot to say. So just to finish up, I just wanted to say that non-aqueous redox batteries, do they have a future? yes, they have great potential. They've got this wide potential window. They've got low temperature energy storage and a big design space. There's so much playing around with redox potentials and tunability to really maximize the performance of your battery. But you're against, low electrolyte conductivity, really high specific surface area resistance, high cost offset. Your costs are ridiculous. If you're relative to an aqueous system, you're looking at, free water and really cheap sulfuric acid electrolyte compared to expensive acetonitrile and really expensive supporting electrolytes to make that a conductive solution. So the viability is all being sort of cost analyzed by groups in America, and you can see that you have to have such incredible performances and specific properties to your complexes to make it viable as a species going forward. So I don't personally think non-aqueous flow batteries are the way forward for energy storage. And that is me. So this is, I just want to acknowledge the group again, and also these two guys whose work all comprise this talk today. Thank you. Sorry I've overrun. Told you I would.
Perfect. Now you're on the 1 hour schedule. Perfect. So yeah, thanks a million. That was a fantastic talk. Really good. I'm going to run out now and make some inorganic friends immediately. And start.
Oh, this guy. Go make friends with this guy.
This guy, okay.
He's a superstar. Cool. I mean, Craig's fantastic too, don't get me wrong. I love you, Craig, if you're there. I don't know if you're watching, but...
So maybe you can stop sharing your screen and we'll see if anyone has any questions.